I'm Becca. I'm one of the 412 instructors in case we haven't met. So what I want to do today is sort of summarize what we did last class and draw comparisons between groups and rings so we can use our intuition from rings to translate to groups. Because the whole basic theme of this class in abstract algebra is the idea of abstraction. In the first half of the class, we started with the integers and we abstracted them. We distilled them down to some basic properties to obtain rings. And we're going to now take this further and consider groups. So we saw last time, and from our reading, that a group is a set with one operation. In comparison to a ring, which is a set with two operations. And we know by the definition of operation that our set has to be closed under that operation. So when I combine via our operation two elements of the set, I get a third element of the set. By the way, in terms of rings, we refer to our two operations usually as multiplication, addition and multiplication. In terms of groups, we don't have a general name for the operation, though sometimes we call it multiplication, sometimes we call it star. If we really want to be precise, we would say that we take A and we apply the binary operation and get B. But usually we'll just write A, B, and we'll often call that times when we're referring to elements of a group. Okay, so we know from our reading that the definition of group has fewer axioms than the definition of ring. And in particular, a group must have an identity. When we looked at rings, our rings had to have both additive and multiplicative identities. We called the additive identity 0, and we called the multiplicative identity 1, usually. In terms of when we're looking at groups, there's only one operation, so there's only one identity. We often call it E, or sometimes we call it E sub G to denote the name of the group. We also require that every element of a group has an inverse. When we looked at rings, all elements had additive inverses. But it was not the case that in a general ring that all elements had to have multiplicative inverses. That was only true in fields, assuming our ring was also commutative. So it is not necessarily true that all elements have multiplicative inverses.
0 doesn't?
Oh, yes, thank you. In fact, thanks, Ava. 0 never will have a multiplicative inverse. 0, the additive identity, never will. The final property in the definition of group is that a group, the operation must be associative. This was also true for rings. Both addition and multiplication had to be associative. And in general, this is the hardest property to show. But if we're able to think of the elements of a group or a ring as functions, we can use the fact that we've already proven that function composition is associative to sort of get around this one. Because in general, showing associativity is really hard. So the goal is to show function composition. or use function composition. We've already observed two groups. We observed D3, which was the symmetries of the triangle. In other words, symmetries means functions of. And if we think of D3 as symmetries of the triangle, they're functions of the triangle, therefore D3 is automatically associative, or the operation on D3 is automatically associative because the elements are functions. And then S3 we thought of as functions from, or permutations of, x1, x2, x3 to itself. And these are also functions, and so the operation could then be thought of as function composition, which again we know is associative, and we don't have to prove that it's associative. In general, this is really hard. Okay, so I wanted to highlight that that's our way of getting around associativity. And one thing that I think is really beautiful about the study of group theory is that every group can be thought of as functions or symmetries of some object. But one of the really challenging aspects of studying groups, and I mean on a research level and on a class level, is figuring out what a group is consists of functions of. Figuring out what object the group translates or is symmetries of. And so this, I think that this is really, really a lot of fun. Yeah, so this is a statement that's true of groups and not quite as true of rings. I'd also like to highlight that when we looked at rings, we had one more property, and that was distributivity. But it doesn't make sense to study distributivity for groups because distributivity was a way of combining the two operations, and when there's only one operation, that just doesn't make sense. Okay, so this is sort of a comparison between the properties of groups and the properties of rings, but I'd like to highlight one of the major advantages of groups over rings, and that's solving equations. By the way, you can tell I'm biased towards groups. So AX equals B. In a ring, this equation did not have to have a solution. We saw plenty of examples of this. I encourage you to think of such an example. But in a group, AX equals B always has a solution. Here I want A and B to be in my group. And why is that? Well, every element has an inverse. So A, in particular, has an inverse. A inverse is in G. So I can multiply on the left by A inverse, and I get A inverse AX equals A inverse B. And I know that this must be equal to the identity. EX equals A inverse B. And because this is the identity, I get that AX equals A inverse B. And this is an element of G. So because every element has an inverse, I can solve equations like this one in groups where that wasn't possible for rings, at least not when I was using multiplication. Okay, thank you.